All right. Well, now I'd like to summarize the properties of the electric and magnetic fields that we've talked about so far. We're going to bring them together into a set of equations that eventually we'll call Maxwell's equations. Only right now we don't really have them quite in final form, as we'll see. So I'd call what we're talking about now Maxwell's equations before Maxwell. All right? Here, let's see what we've got. All right. So far, we have the following. We know that the divergence of the electric field is given by rho over epsilon naught, sometimes called Gauss's law, okay? And we found the curl of the electric field. In electrostatics, it was 0, but now we know that this is equal to minus the rate of change of the magnetic field, okay? Similarly, we know that the divergence of the magnetic field is 0. And we have the last equation, Ampere's law, which tells me that the curl of the magnetic field is equal to mu naught times the current density. So this set of equations is at the heart of electricity and magnetism. Oh, excuse me. And, well, this is what they look like so far. Okay. Now, we've derived these from our discussions of electrostatics and then magnetostatics. But it's not clear if these are still correct in electrodynamics. In particular, we derived Ampere's law for the case of constant currents, all right? And it's not clear if Ampere's law is still valid in the case that the currents can change with time. So that's what I'd like to investigate next. And what we're going to see in a moment is that there's a problem, okay? Here, I'll illustrate the problem before we start talking about it in depth with this drawing. Here, in this circuit that we're going to look at in a moment, we have a voltage source like a battery, we have a switch, and we have a capacitor. Imagine that we close the switch. For a short amount of time, a current will flow in the circuit, right? As the capacitor charges up. Of course, once the voltage across the capacitor reaches the battery voltage, well, then current will stop flowing. But what about in this short period before it does? Well, in that period, we have a current flowing through the wires, and we have charge building up on the capacitor. And the question I'm going to ask is, what's the magnetic field around the wires? Here. For example, what's the magnetic field right here, or right here, or right here, above the point between the capacitor plates? What I want to show you is that there's kind of a problem with this. Ampere's law lets us calculate the magnetic fields around a flowing current pretty easily. And if we draw an Amperian loop here, why, it certainly encloses a current, and so we expect a magnetic field. And the same thing is true over here. But what about right here? Of course, there's no current flowing inside of the capacitor. There's only current flowing in on the left, charging up the left plate, and out on the right. But there's no current that flows through. So is there a magnetic field at the point that I've indicated here? Well, Ampere's law here seems ambiguous. And I want to look closely at that and convince you that this is a real problem, not just a problem with my drawing. And let's do that in the next video.